Our next speaker has over 20 years of experience in software engineering and security best practices and is passionate about improving the state of cybersecurity at the earliest stages of software development. We present Brice Williams with Weaknesses in Security Testing.
Thanks, Rob. Welcome, everyone, to Weaknesses in Security Testing. This talk is about application-level security testing and weaknesses in test automation. My name is Brice Williams, and I'm the cybersecurity practice lead for a technology consulting firm called SysLogic. I've had over 20 years of experience in software development and cybersecurity, and I lead a team of security consultants who performs penetration testing of commercial products, applications, IoT, IIoT devices, as well as trains thousands of developers around the world. I'm based here in New York City, and I've really enjoyed attending HOPE over the years, and I'm excited to be speaking at this year's online event. I'm going to be using two different main information sources for this talk. One is from the data from the pen testing that SysLogic has performed over the years. We perform a variety of product and hardware device assessments that involve detailed review of really everything that the client will give us: source code, documentation, configuration, virtual and physical environments. Over the last decade, we've evaluated many different types of products, several different industry verticals, many millions of lines of code, thousands of security weaknesses reported. The other main area of information that this talk derives from is the Open Web Application Security Project, or OWASP. If you're not familiar with OWASP, it's a global organization with a lot of great resources. Some of those are listed here that I've derived guidance and just general information from. For example, the Application Security Verification Standard, I'll talk more about this one. Mobile Application Security Verification Standard, Web Security Testing Guide, the Mobile Security Testing Guide, and the Firmware Security Testing Methodology. If you're not familiar with these, I highly recommend that you check them out just to give you more information about what goes into building software securely, how to test them, to look for security weaknesses, and even leverage that information from more of an attack and exploit point of view. The OWASP ASVS, or Application Security Verification Standard, is currently at version 4.0. It consists of 288 granular security requirements and has two main purposes: to help organizations develop and maintain secure applications, and to allow security service vendors, security tool vendors, and consumers to align their requirements and offerings. It contains a very interesting statement in it. Automated tools and online scans are unable to complete more than half of the ASVS without human assistance. I won't go into detail about this chart on the lower half of the slide here, but there are three different levels. Level 1 is designed to be penetration testable. Levels 2 and 3 require access to documentation, source code, configuration, and the people involved in the development process. So those are the types of requirements in those levels that are generally not something that automated tools can detect. So certainly quite a number of requirements in this excellent resource that tools aren't going to be able to assist with as easily. My team and I did a review of the pen tests that we performed over the last decade or so, and realized after going through all the data that on average, almost half of the vulnerabilities we discovered were found through manual analysis, meaning that the others were either found by automated tools, or at least the tools provided enough of a direction for us to dig in and find that particular weakness. So that's a large number of findings, and your mileage may vary, but that's what we saw. We also noticed that our manual findings had a higher average severity. We also noticed that more manual findings were in IoT device assessments and with more secure systems, which makes sense. Those systems that are more mature have had multiple pen tests performed against them. Likely at that point, we're only finding elements through manual means. So what does this number mean, this 46%? Maybe my team didn't use the best tools or could have configured them better, but like many teams, we're constantly updating our tool set and looking for better ways to automate what we do. My guess is that other teams would have a similar percentage, whether that's 30% or it's 50%. I think a good amount of findings as a result of a pen test or a particular security assessment are those that can only be found via manual means. This next slide looks at pen test finding categories. This chart's based on vulnerability types per pen test. So you can see on the left-hand side, we have more third-party based findings as opposed to access control, for example, on the far right. That's to be expected. A lot of modern software uses a lot of open source. So that open source has published security vulnerabilities in them, so a good number of the findings likely fall into the third-party category. Security tools tend to have a lot more findings in categories that they do well in, and less findings in categories that they struggle with. The same is true for pen test engagements, where you have a lot of team members and different types of tools and manual analysis that's performed, but certainly to a lesser degree. So this is interesting data in the sense that it shows, based on our data, what our breakdown looks like by category. This helps us understand where we need to focus, either having better tools or better processes and techniques for finding weaknesses in areas where we don't see as much. Certainly, at the end of the day, the applications that we review that simply may not have as many weaknesses in certain areas than they do in others, but you can at least see what we were able to produce. In this next section, I want to talk about different types of security testing tools. First, we have static application security testing, or SAST. This is the analysis of computer software without actually executing programs. It includes source code, binaries, mobile APK IPA files, container images, firmware images, etc. So it's not just source code analysis, although we often think of SAST as being source code analysis. It could be more than that. It can also be as simple as grep-like tools to powerful solutions using data flow analysis and machine learning. Some common SAST tools, CPP check, Find Security Bugs, ESLint, SonarQube, these all have open source versions that are a great way to get involved in the SAST testing area. Commercial tools in this space can be rather pricey, which is why many use open source tools. Next, we have software composition analysis, or SCA. SCA tools examine software to determine the origins of all components within the software. They're effective at identifying open source libraries with published vulnerabilities. So they don't look at open source library code, for example, and find weaknesses necessarily that haven't already been discovered. Their whole purpose is to create an asset inventory of all of your open source libraries and identify if there are any known published vulnerabilities for those library versions to help you make the appropriate steps around upgrading or applying a patch. Some common tools we see in this space include npm audit, dependency check and dependency track, which are both OWASP projects, and retired.js, which is great at scanning your JavaScript libraries. Next, we have dynamic application security testing, or DAST. This typically refers to web applications and APIs while they're running in a production or a production-like environment. DAST doesn't have any view into the internal workings or source code of the target. It's purely looking from the outside. It uses many of the same techniques as an attacker would to find potential weaknesses in a system, which makes it very valuable in your test arsenal. Some popular tools are Zap, Burp Suite, and Arachne. Interactive Application Security Testing, or IAST. IAST tools use a combination of both static and dynamic analysis techniques. They can test whether known vulnerabilities in code are exploitable in the running application. They use knowledge of application flows, data flows to create advanced attack scenarios and use dynamic analysis results recursively. In this diagram here at the bottom, you can see a kind of a typical DAST scanner is one component of the solution. Then you have your application, which is instrumented or it has IAST agents installed on a virtual machine or in a container. And then there's a management service or something that collects the results or the telemetry data that's collected about the particular attack and has much more context about the attack as it's occurring. Let's look at some areas where tools do well. First, we have memory safety, insecure string and integer handling, and ASLR, DEP. These are all things that a good static analysis tool can help with, especially in the C and C++ space, looking for memory-related concerns in the code, insecure string handling, use of binary protections as a result of compiler flags to opt into operating system protections like ASLR and DEP, all things that are very easy for a good static analysis tool to do and to do well. Identifying open source software and their published vulnerabilities. This is where your SCA, your software composition analysis tool, is really good at creating an inventory of the libraries that are being used, letting you know if there are any published vulnerabilities in those versions, even highlighting if there's license concerns based on policies that your organization might have, something those tools do quite well. Common web issues like XSS, CSRF, clickjacking, missing security headers, these all fall into the realm where a DAST tool is really useful and can detect these sort of items very easily right away, even with just some passive scanning in many cases. Then we have injection weaknesses. SQL, XML, LDAP, OS, there's many different type of injection weaknesses. You can find these through a variety of means. A static analysis tool can often find these based on the particular language. A DAST tool is also quite useful at exercising and finding injection weaknesses if it's a web application. But the tool that does this best is the IAST tool, in that it can not only do what the DAST and SAST tools do, but it can also find where maybe the development team has done something a little out of the ordinary. They've used a unique framework or some custom layers to their process so that it would be more difficult for a SAST or DAST tool necessarily to see this issue. But if especially if you were to do some manual kind of poking and prodding on this from the outside, that's where the IAST tool would likely be able to detect that an actual injection issue did occur or is possible and notify you of it. And there's certainly many more areas where tools can do well. Just wanted to highlight a few here. Here are some common misunderstandings about security tools. I've seen a number of organizations that are too reliant on tooling for their security health, and many of these things come up at times. For example, that one good security tool can do it all. I wish this were true, but it almost never is in any environment. Many teams, more mature teams, have multiple tools, a variety of tools in their arsenal. That higher cost means better results. Certainly, higher cost tools can be worth the price tag, but that doesn't mean that just because you pay a lot of money for a tool that it's going to meet your needs or meet all of your needs. Oftentimes, open source tools can be just as good in the right hands. That they can be used by those with little security experience. Generally, tools do require a level of experience either with using the tool itself or with cybersecurity related concerns or maybe software development best practices. That you always want zero false positives. This can be a little contentious at times, but I like to see at least a few false positives, a minimal set, but at least a few, kind of depending on the engagement, because those often will clue you into something that could be a little suspicious, things that require investigation. So if you have no false positives, likely you're excluding even suspicious related areas of the code or the system, where if you dug into it a little deeper, then you might find something. The tools can replace people. This certainly is not true. We will always have people involved in security testing. Tools just help to make their job a little easier. And the results are generally understood by software engineers. Some tools do a better job of this than others, but often the results that come from a security tool need some level of translation. They need some way of, turning it into a language that developers can take and make actionable changes to the system in order to correct that flaw. So in this next section, let's look at some examples where tools fall short. First, we have poor architecture choices. On this image on the left, you can see that lower balcony has no way to get to it. So whatever the purpose was behind this, it was at least not a very good design. Automated tools generally have a hard time getting enough context to point out design flaws. It's very often that we see a general lack of reusable security protections, meaning if you can't find session management weaknesses in a particular device, you might find them in another device from the same manufacturer. One example that we've seen many times is that applications use custom implementations of identity and authentication services instead of leveraging a more secure third-party solution. We almost always recommend that software engineers take advantage of something that's well vetted, provides a good authentication solution rather than building their own. Insecure Direct Object Reference, or IDOR. IDOR weaknesses are a type of access control vulnerability that arises when an application uses user-supplied input to access objects without verification. For example, in a multi-tenant systems where the user is not verified to ensure they have authorization to access the requested tenant ID. So in this URL at the bottom here, you can see the ID parameter takes an integer value. What happens if the attacker changes that number to a different value that the current user shouldn't have access to? This is something where security tools, they can fuzz that ID and tell you if anything bad happened, anything out of the ordinary, an error occurs, but they can't really tell you if the data that you're getting should be returned or not. This is often overlooked by software engineers because they assume an attacker would not be able to determine the ID of another object or another tenant, something the user shouldn't have access to. Administrative access control. How does a security tool know what is admin level functionality? Should a user be able to view details of other users in the system? That's one example of what could be administrative access in one system, but not in another. So it can be difficult for tools to really help here. They often provide limited help in determining if authorization checks were correctly implemented. We've seen custom authorization implementations generally have weaknesses if you poke at them deep enough. For example, in a poor implementation, we'll often see a scenario where a user can upgrade their role or permission simply by, changing a parameter or supplying a field where, maybe the UI isn't passing it to an API, but if you supply it, you could change your role to an administrator, and there's no authorization check to prevent that from happening. A tool might be able to help with this, but they generally don't, so it's kind of up to you as you're evaluating a system to see if something like this is possible. Next, I want to look at an access control example. We did a particular pen test where the system had a fairly complex authorization model. And we noticed in our testing that there were some discrepancies between the user accounts and the roles that they were assigned to and ultimately the permissions that they had. In this case, in this system, the permissions were called features. We noticed that regardless of what user we were testing with, we had access to the same sort of permissions and things in the system. So we went through and did what we call a detailed authorization or access control review, where we looked at all of the API methods that you could call as a user, or the application would call on your behalf, and then all of the roles and the underlying features that were defined in the code and mapped them all out in a spreadsheet. And we highlighted two interesting things. One, these lines in yellow, which I don't expect you to be able to read this, it's rather small. The lines in yellow were features that included unexpected API access. So what that means is that the feature had a name like miscellaneous or connected equipment, which isn't very instructive about what it should allow the user to do. So that when you're assigning these features to roles, it's not entirely clear what it is that you're assigning that role to be able to do. More concerning were the ones that we highlighted in pink here. And these were features that provided some sort of administrative access, where again, it wasn't clear based on the name of the feature that it was providing any sort of administrative access. It's not clearly named admin or like user administration. In this case, again, we had feature names like miscellaneous or connected equipment. So it was somewhat confusing, not only from a naming perspective, but we also saw that some of the API methods didn't have any features at all assigned to them, meaning that all the users had access to them and they were administrative functionality. This is a good exercise to do. Many systems, especially those that are more mature over time, they've developed this bit of complexity to their authorization models. And with complexity comes confusion and ultimately the possibility to create insecure scenarios, especially where end users of the system don't understand what they're assigning to users, or you have some permissions effectively that slip through the cracks. Misuse of cryptography. Tools can highlight lack of encryption, use of insecure or weak ciphers, and misconfiguration issues. What they're not so good at is determining whether you're using the wrong tool for the job, like reversible encryption to store user account passwords, instead of using like a password-based key derivation function, which is preferred. Tools are also poor at telling you when encryption keys are not being stored securely or being reused between environments or devices. We see this quite often in systems. Let's look at an example of poor cryptography. Here we have two pen tests of the same system. In the first pen test, we discovered some sensitive data that was being stored in HTML5 local storage. So this was a web application. HTML5 local storage is insecure when it's used on a shared computer. If someone closes the browser, that data will still exist on that particular computer. So if an attacker had local access to it, they would be able to recover that data. We reported this to the software development team, said, hey, instead of using HTML5 local storage to store this sensitive data, like access keys, instead put those into HTML5 session storage, which is cleared when the browser is closed. So on the second pen test, we found out that the developers addressed this by encrypting the HTML5 local storage using a static encryption key that was stored in a JavaScript file accessible to anyone. So in other words, they didn't follow our recommendations. They decided instead to apply some crazy encryption that, took a little bit of time, but we could figure out just by looking through JavaScript files how the encryption worked, where the key was stored. This is almost never the right way to do this, and it's very difficult to do this securely, maybe impossible in some people's opinions. This is definitely an area that tools would struggle with, showing a particular problem in this case. Next, we have Credential Recovery. And we're looking at a table here that contains a list of items from the OWASP Forgot Password cheat sheet. OWASP has a number of cheat sheets, which are effectively checklists of things. If you're designing a system, you want to make sure that you keep in mind in order to make that particular system or component more secure. So in this table, we have a few from that checklist, along with tools used to help detect a weakness in that area or not. So for example, you really should return a consistent message for both existent and non-existent user accounts when you're supplying, say, an email address or a username, and you want to receive something to help you reset your password. Tools technically should be able to help with this, although most that I've seen cannot. You should also make sure that the time taken for the user response message is uniform. If there's a big difference in time between user accounts supplied that exist versus those that don't, an attacker can use that information to determine which accounts exist in the system. This is another area where tools should be able to help with, but generally we don't see this in tools. You should use a side channel to communicate the method to reset their password. This will be very difficult for a tool to detect and tell if it was done correctly, simply because the tool doesn't have that context. It can't tell that an email message is being sent out or an SMS message is being sent out. It can't look at those tokens necessarily to see that they're being supplied, that they're stored securely on the back end, that they're single use and expire after an appropriate period. All of the things that involve forgot password recovery. Most of the things around being able to recover your password is something that security tooling is going to have difficulty in telling you if it was implemented securely or not. Sufficient auditing. There are many things that can go into robust application level auditing, most of which tools cannot help with. For example, application audits all relevant user actions. It would be difficult for a tool to be able to tell you if you have enough logging or that you're logging the most important areas of your application's use. That the time clock is properly synchronized. Make sure you've got accurate timestamps on each of your audit entries. That the application uses a global unhandled exception handler. This is something that a tool might be able to help with depending on the programming language and the context, but generally I don't see this in tools. That each audit event includes a user ID or a username or something of that nature. Also that each audit event includes client IP, anything around determining if audit events are robust enough. They include the data that you might need later for incident response work. That's something that tools generally aren't going to help with. That audit logs are adequately protected from tampering. This is another area where tools generally cannot help you. Mass parameter assignment is a very interesting sort of attack. This is an area where I think tools could help more with, but they generally don't, and so it's often something that you can look for in systems to see if this is a possibility. The way it works is some software frameworks allow developers to automatically bind HTTP request parameters into program code variables or objects to make things easier for the developers. So in the example below, we've got a HTML form. We can see 3 different values, user ID, password, and email, that are submitted via that form. And then this class we see, this user class, is on the back. This is what is receiving that data that's inputted by the user. And you'll notice there's an additional property here, this isAdmin. Certain web frameworks will automatically bind the isAdmin property, or really any property, if it's supplied by the front end, by the HTML form in this case. It handles wiring that up automatically, which is convenient, but also can open up the door to security issues. Like in this case, if an attacker knew or they simply guessed that that particular property might exist, they could supply an isAdmin equals true and potentially change the user's role from a general user to an administrator and thus elevate their privileges. Business logic attacks. Tools can help replicate bots and automation attacks, but they need you to guide them on what activity is considered unacceptable if done too quickly or out of sequence. This is another interesting area we see in applications, not quite as frequently, but definitely an area where tools are not going to be able to help much. In this particular example below, it's called a time of check to time of use attack. And here we have an IoT device that can be updated via a USB or SD card, which contains a digitally signed firmware upgrade. So a user can supply that to upgrade the device. And in this particular workflow, the attacker supplies a valid firmware file via a USB or SD card, inserts it into the device. The device then validates that the signature is correct and then prompts the user. So at this point, it pauses, prompts the user to say, hey, do you want to continue? We've validated the firmware image. It's good to go. Normally, what would happen is the user would choose yes. It would go ahead and install that firmware image and everything would be fine. But the attacker at this point can remove the SD card and replace it with their own containing a firmware image of their own that they have not signed. And in this case, because the validation check was already done, the process thinks everything's fine. So when the user clicks OK, it continues, and the device is now running bad firmware. This is simply a workflow in which, if done out of sequence, or the developers aren't thinking through scenarios in which an attacker could change things or do things unexpectedly, you could result in an insecure state like what we see here. Secure configuration. A lot of application security is controlled through configuration settings outside of the code. Many tools overlook these settings. Some can certainly help, but you often see issues, especially with like custom configuration settings, which in turn control how security is handled throughout the system. Security tools might be able to help with common security configuration and can highlight those, but anywhere where you've got anything that's done in a more custom basis, that's where it's going to be difficult for a security tool to help you, because all it can do, like in a static analysis scenario, is look at the code and say, well, in some cases, it looks like it would be set fine. We often see the same backend keys or passwords used in both test and production environments. And this, of course, allows attackers to take information that they learn from a test environment and apply it to a production environment if they have that sort of access. In this configuration snippet in the lower right, we see some common configuration settings like this. Redirect to HTTPS is set to false when it really should be true, or validate SSL certificates set to false when it really should be true. Often these are set this way for like development environments where they turn off security in order to ensure functionality is working. And then they might forget to turn these settings on in a production environment, or there might be certain conditions where these settings don't apply. And so that's where things can, get it into trouble. As a result, it's very important to pay attention to security or just configuration settings in general and make sure that security is not being turned off, bypassed, or downgraded as a result of those settings. Substandard protections. Often we will see that software engineers will add security protections to a particular application or product that are a little abnormal, a little unusual, and as a result often have weaknesses. And those weaknesses sometimes are not something that a security tool can find, but certainly something that you can find with a little bit of effort. Often we see that developers might get notified of a finding because of a security tool, but then they'll make a change to address that just enough so that the security tool likes what it sees, and as a result, they can continue on with their day. But they haven't really addressed the underlying problem. They just put a Band-Aid on it that a skilled attacker can find another way to exploit. So in this particular example, this was a very interesting one. It was an IoT device. It had a web interface and a Node.js backend. And this may be difficult to read here, but on the left-hand side, there's a verify password function. And they had put in some protections to prevent OS command injection. If you look closely here, you can see if the password length is greater than 16 characters, it will give a message that password length greater than 16, rejecting. They also look for certain special characters. And if they detect them, it will print out OS injection character rejecting. Ultimately, the password and salt value that's passed to this function is passed along to the OpenSSL passwd command line in order to create a value, effectively hash the password, so it can then compare it to what's stored in the underlying user account store. What we recognized after looking at this code was that certainly this is good enough to prevent most like DAST tools from finding this sort of issue, but not good enough if you're really clever and can work through the fact that you have specific limitations, but they haven't closed off everything. So for example, you can still use the backtick character. So as long as you can send commands that are 16 characters or less, you could still potentially take advantage of running your own OS commands. So effectively, that's what we did. We sent in, took us a bit to figure this out, but we sent in a series of password submissions. In other words, this was a login page, and you could give it a value as the password that it would then ultimately pass to OpenSSL via the command line. So effectively, we wanted to terminate that command and run our own command. So we passed in a series of just short characters and built up little script files. We needed an ampersand character, but that was in their exclude list. So ultimately, we had to build our own little script that would convert exclamation point characters to our ampersand. Then we built another bash script here that would open a reverse shell. And so ultimately, we ended up being able to get this to execute via a remote netcat listener, had remote shell access to this device as root, all just by taking advantage of a fairly simple weakness in a login page where they already had protections in place to prevent against OS command injection. This is just a good example of areas that we see in systems where there are some protections in place, sometimes just enough to get past the results seen by security tools, but not good enough to prevent an attack from someone who's skilled enough to understand how they can manipulate the system better. In this next section, I want to look at some suggested ways to improve. First off, we have better security testing. If you perform manual security testing, or maybe you participate in bug bounty programs, I recommend that you focus on areas where tools don't do as well. This will give you more opportunity because you'll be able to focus on things that tools will overlook. Some of that low-hanging fruit that they're good at, you'll be able to get the more difficult items or the things that tools just aren't good at finding. If you build security testing tools, add features or new tools to address gaps covered in this talk. All tools have room for improvement. Next, we have cybersecurity training. Training for software engineers is my #1 recommendation for improving cybersecurity health. This slide has 3 different methods just to highlight different styles of training. They all have their pros and cons. So for example, instructor-led or classroom-style training has great personal interaction. It's the most widely used type of training, maybe more difficult to scale. This is the type of training that SysLogic provides to software engineers, both on-site and remote. And with the current pandemic, everything's being done remote, so this is totally understandable to be able to provide this remotely and be able to do so in a way where attendees are able to retain knowledge easily. Next, we have recorded or e-learning. Scales well. You can take it at your own pace because you're just leveraging some pre-recorded content. You, of course, have lower interaction at this point. Then we have hands-on labs. These are practical. They're well-liked. Generally good retention because you're getting in there, you're doing something, and as a result, you retain that knowledge much better. These often require longer or on-site classes, not always, but certainly if you're working with IoT devices and attendees need to have those devices, then you can't provide those as easily. On the right-hand side here, I wanted to highlight some various services, some commercial offerings out there that provide great hands-on style training, either writing code and understanding how to do it more securely, or looking at vulnerable code and identifying weaknesses in that software There's just some great resources to check out if you want to see what's available for providing hands-on training, gamification, CTF style to your software engineers. One I'll highlight is OWASP Juice Shop. This is a free vulnerable web application that's designed to teach you how to discover weaknesses in systems. And it does a great job of providing a modern web application that not only has weaknesses in it, but does a great job of telling you, kind of giving you awards when you find those weaknesses. And it can be used more in a CTF style environment where you have a team that are competing against each other. Unit and integration testing. I wish that security-focused unit and integration tests were more common. Unfortunately, they're not, but this is a great resource for software developers to take advantage of. So when a type of vulnerability is discovered in code, developers should consider writing automated tests that continually look for other instances of this vulnerability. This is really powerful with custom frameworks that a static analysis tool would not be aware of or have necessary context to work with. So you can build automated security tests to leverage security tools in a more targeted fashion that often provides that much needed context. This is something that I recommend to development teams that have, they've taken care of the basics. They need to move up to that next level. They've run security tools. They've, addressed all of the findings on an automated basis in their CI/CD process. The next step that I recommend, get those security unit tests, those security integration tests in the system so that you look for things that are specific to your software, to your frameworks that are being used. Next, we have application penetration testing. And I want to highlight that this does differ from your traditional pen testing that looks at, an organization's network environments or their Wi-Fi networks. One of the main goals, of course, is trying to get domain admin credentials in that case. With an application pen test or a product pen test, you generally are looking at the holistic view of the system, ideally. So there's generally some research and discovery that occurs, understanding how the system works, looking at architectural documentation, looking at threat models or producing threat models of the system. Then there's some automation involved. That's where you run your tools, scan for various weaknesses. You also want to look at source code, make sure that's thoroughly reviewed. And of course, manual analysis that can take a variety of forms depending on the system, but just, poking and prodding at the system to try and understand where there might be weaknesses. And then at the end, providing some remediation options. It doesn't work as well if you don't provide information that is actionable by the software developers, if they can't address the weaknesses that you're identifying. So take some time, understand what they need to change, what they need to do, and provide some pointers, some guidance, or as explicit as you can be in terms of, make this configuration setting or change this code to this or use this other third-party library to provide this functionality. The more you can give, targeted guidance, the more likely it is that developers are going to be able to address that issue or at least address it more quickly. And it's also important, of course, to sit down with them and talk about the results, answer any questions that they might have so that they have a full understanding about the weaknesses that were discovered and how they can address those so that the next time that you look at the system, assuming there is a next time, and ideally there is, that you can see that those past vulnerabilities have been addressed and they've been addressed well. So I spoke about that from the standpoint of someone that's involved in penetration testing. But if you're on the other side of the fence and you're working with pen test firms, take a look at what their process is and see, do they have these various steps, or how detailed are they being in their pen testing? Maybe you don't need this level, you're wanting to just do a cursory level review of the system, but just know that generally the more information that you can provide and the more that they can spend time going through various components of the system, the better results that you're going to get. Bug bounty programs. For those not familiar with bug bounty programs, they're a deal that's offered by many organizations by which individuals can receive recognition and compensation for reporting security bugs. They work best for organizations that have achieved a more mature level of security practice, so I wouldn't recommend these for the organization that is really just getting started down their security path. If you have trouble patching your servers with security updates, then a bug bounty program is not for you, not yet. Skilled bug bounty testers can almost always find weaknesses that tools would overlook, so make sure that you've run the tools first to identify issues. When you feel pretty comfortable that you found everything that tools can find, then you can hand it over to bug bounty testers who are likely going to take it to that next level and hopefully find issues that are deeper, require more time, more expertise in particular areas. In conclusion, I want to leave you with 3 points. 1, that most applications in IoT devices have security flaws. This will almost likely be the case for some time to come. Number 2, that security tools have plenty of room for growth. And number 3, if you're in the business of exploiting weaknesses in systems, take a look at areas where tools tend to struggle with. This bit.ly link here on the left-hand side will get you a copy of this presentation. And I just want to thank everyone for attending my talk today, and I look forward to your questions.
And we'd like to present Brice Williams live and direct. This is Weaknesses in Security Testing. And now that you've seen the presentation, we'd like to invite our audience, those of you in the Matrix chat room, you are welcome to ask your questions to Brice. Just type them out in the channel and we will relay them here. That is the session Q&A channel on our Matrix server.
Thanks everyone that was able to listen in. I really appreciate the opportunity to share some of my experience and my team's experience. And if you have any questions, that'd be great. Happy to answer them. This was obviously a fun experience for me. It's always interesting doing an online recorded version as opposed to a live event.
It's interesting. We're presenting to more people than we could fit in a ballroom at the Hotel Pennsylvania, so that's cool. And if any of you in the audience have questions, please present them.
Yeah, I know my team has. This is something that we talk about on a daily basis. This idea of testing software for security weaknesses, using tools, liking tools, hating tools, trying every technique possible, saying, why isn't there a tool that does this? Can we write it? Sometimes we can, sometimes we can't. So this will obviously be an area of continued improvement over time. So I'm not so pessimistic that I think that this is, that this is an area where we will never see improvements and tools are terrible. No, tools are very good and very useful. It's just that it's interesting when you think about what can a tool do versus what it can't do and where you have to augment that. And so as a result that, it's good for us that us humans that make a living off of this.
We do have one question from the audience. An audience member says, we get bad rep with devs. They feel like what they're doing is pointless or don't see the reason for it. What recommendations can you give security practitioners to get devs to consider and involve security from the beginning?
It always is challenging to help the development side of the house understand your motivations. You want them to be able to feel like you're trying to help them. So I think the more you can communicate towards the end goal of, hey, we all want to make the system more secure, and acknowledge that you may not understand what it takes for them to fix a particular problem. So you want to learn, you want to understand what are their challenges, because they're balancing a lot of priorities, deadlines, usability, performance. We have these conversations all the time. It's helpful that, I have a software development background. Most of my team members also do. So we can kind of relate and understand that, hey, we'll give you a recommendation, but we know that there's a lot of caveat to that. So here's maybe a couple of other options, or come back to us. Let's talk about it in more detail, or maybe we'll point them to someone else within the organization that has done this successfully. So we'll say, go talk with them because they have likely a good solution or something you can start with as a reference point.
Interesting. Someone asks a very short question, DMZ, yes or no? Pros of yes, pros of no?
Yeah, I'm all for DMZs. I mean, there's a lot more to that answer, I think, based on the context of the system. But yeah, DMZs are generally a good thing. I mean, your basic cybersecurity concepts are almost always going to be true, regardless of the system. For example, the things that we test for and look for, like in a modern cloud-hosted, containerized, orchestrated system, is in many ways somewhat similar to things we look at in an embedded IoT system. Obviously, the technology is different, but the core concepts are the same. You still have authentication, you still have authorization, you still have to protect secrets, and so on. Great question, though.
Indeed. Just for the sake of those unfamiliar, how would you explain the idea of a DMZ?
A DMZ, or demilitarized zone, it's essentially a kind of a sandboxed area where you, on your perimeter, usually with like a web application or something that you're exposing to a hostile environment like the internet. And the idea is that your traffic hits some service or server in your DMZ, which has more of a it's more of a hardened environment, has limited attack surface, has more security controls involved. And then your more sensitive systems, maybe systems that haven't had the rigor or of security controls in place, are on the back end. So your DMZ acts as that buffer between the front end, where you're receiving requests, and your back end. So systems like a web application firewall is something you generally would see in like a DMZ, whether it's a dedicated DMZ you set up or it's kind of implied based on your cloud provider. But that's the type of system that's nice. And some of the benefits of having something like that is maybe any items that are in your DMZ, or like a WAF, for example, can be controlled by your production team or your infrastructure team, which might not be your software development team. And sometimes there are benefits there. You can make changes more quickly. It doesn't have to go through the same change control, less people involved. So there's certainly pros and cons with it, but I definitely see benefits in having those sort of perimeter defenses, including use of a DMZ.
Okay, we've got a few minutes left. One more question. Do you ever get pushback on recommendations because something is, quote, too obscure to be used because of the use of older technology stacks?
All the time. We get pushback. And some folks we work with are great. Others, I swear I can give a response to them. And we do this thing we call retesting, where they make a change or they come back with like an explanation, and we kind of just verify it as an outside, third party. And there are times where we've gone back and forth 5 times. I'm like, they are totally not getting it. First, I think it's a problem. Maybe I'm not understanding the sort of solution. So I ask for, more information. But yeah, quite often, not all the time, but there's a couple cases where we get some significant pushback. And in those cases, we want to make sure that we take the time to back up our reasoning. So provide, sources to guidance that's not just us. For example, recommend OWASP or recommend, resources at NIST or whatever, to say, hey, don't take our word for it. Look at what this particular standard is or this best practice. That way they're not, maybe they're having a hard time hearing it from us, and we can direct them to someone else that maybe it just works better, or find some advocate for us within the organization. Sometimes it's just personality differences. There's, as you can imagine.
And as we wrap this up, where should interested people go if they want to find out more about what you do and get in touch?
You can certainly feel free to email me. My email's in the link there, or hit me up on Twitter at BriceX. Be happy to provide you with more information or just chat. And obviously the OWASP resources and other things I mentioned are just good in general for learning more about what do software developers need to do when it comes to hardening security systems. And just having that information helps you not only as a software developer, but understand how to provide better information to them, how to look for weaknesses in systems that developers likely are overlooking, and everything around that.
Sounds good. We have time for one more very quick question. Have you tried or seen security analysis tools results being managed directly by devs?
I have, yeah, and there are some very good tools, especially those that like integrate right within like a CI/CD pipeline. They can get those results. So say if the team is using a ticketing system like Jira, for example, if you've got a system that's fully automated and comes back right in their ticketing system, maybe with just like a security flag or tag on it, those tend to work really well. Obviously, they can't find everything. But the more it's integrated and the developers are able to work within their environment, use their tools, their IDEs, I think the better. It goes a long way towards catching things early, and at least that low-hanging fruit, take care of it before it gets out into production or is found by a pen test, et cetera.
Excellent. And with that, I think we'll have to wrap up. We're just about out of time. But this has been Weaknesses in Security Testing. Brice Williams, thank you very much for joining us.
Great. Thank you, everyone.